His research interests include advanced network systems, traffic modeling with application in connected and autonomous vehicles, shared mobility, electric vehicles, etc. He's the first holder of the Suzhou A. Bracken Faculty Fellowship at UCF and is a recipient of the National Science Foundation Career Award. He served as a PI and co-PI for a number of federal funded NSF, etc. Amounting to $7 million. He has published more than 58 peer-reviewed journals, many of which are in the top journals such as Part B and Transportation Science Operations Research. He has served as a member of the Transportation Network Modeling Committee and the Traffic Flow Theory and Characteristics Committee of the Transportation Research Board, and an associate department editor of the IIE Transactions Focused Issues on Operational Engineering and Analytics. Dr. Lee received his BS degree in civil engineering with the computer engineering minor from Tsinghua University, an MS degree and a PhD degree with an MS degree in applied mathematics from the University of Illinois at Urbana-Champaign, where he was working with my friend and colleague Xiaopeng over there. All right, so thanks again for accepting our invitation. You have to know that he just landed from, where were you?
New Zealand.
New Zealand, that's right. 17 hours jet lag. So please join me in welcoming.
Thank you, Dr. Lama, for the comprehensive introduction. So it's a great pleasure and honor to come here and give a talk. And so, despite my jet lag, I'm pretty excited to see my friend Dr. Lava and all of you guys. And I'm going to talk about some of my work related to connected, automated, and also modular vehicles. So we're going to talk about some modeling and analytical properties and some field experiments. So while we enjoy the convenience of the modern transportation systems for mobility, and we are also bothered by some limitations of the system. I think during your morning commute, you probably have experienced long waitings at arterials, signalized arterials, just because you have to wait and stop at the red light, and the traffic forms alternating stop and go patterns. Whether you drive or take a ride or just walk here, you have to take turns to pass intersections and other conflict areas. Even in freeway, in morning commute, probably most of you have experienced this kind of stop and go traffic during early morning peak hours, and you probably can experience that in all of your freeways here, like I-20, 85, I-75. I experienced quite a lot when I was driving around. So such stop and go traffic and cause significant delays to each and every one of us. And as the congestion increases, people get impatient and absent-minded, and then safety becomes an issue. And also, such unstable movements of the traffic stream exacerbates the already high environmental impacts from transportation. So how do we address these issues? I think the perspective we took is from emerging technology. So you probably have heard of connected vehicles. That is a technology for vehicles to communicate with other vehicles and other objects related to transportation systems. And then autonomous vehicles, which means robot drive vehicles instead of human drivers. And we can program their driving rules instead of learning human driving behavior. And also there are some recent technologies called modular vehicles, and this is like physically connected autonomous vehicles. So vehicles can separate and dock together during operations, and then doors between vehicles can open so people can have on-route transfers. So lots of interesting things. And when vehicles dock together, it's like an extreme of vehicle platooning, if you have heard of it. So, except that vehicle platooning is wireless, and people have some space, and the vehicles have some space, and modular vehicles like physically connected together. So with all these technologies, people are pretty excited, and some envision that this kind of utopian world in the future. And it seems like in this idealistic traffic scenario, every object moves smoothly without stopping throughout the systems, even with limited infrastructure. And I don't know what you feel. I wouldn't dare to walk around in this kind of traffic. But that's what people hope. All right, so in order to get from there, I think it would still take a long route. So what are the implications of these emerging technologies to the transportation systems? So actually, before these technologies, and traditional paradigm of transportation engineering research is about accommodating human driver behaviors. So we probably cannot change much about human driver behaviors. We can affect them, but we need to spend lots of effort to learn how humans drive and how to accommodate human drivers safely and fastly, and with minimum environmental impacts. Yet, with such emerging technologies, we may be able to modify the behaviors. For example, driving assistance systems that are already happening in many of your vehicles. How many of you guys have vehicles with adaptive cruise control? Yeah, I see a number of hands in, so that's cool actually. So with adaptive cruise control, if you're turning it on, actually, it's already have a different kind of car following behavior than you drive yourself. All right, but at the same time, you have to control, the other decisions, whether you turn it on or turn it off, what like headway you want to set up, and also, if you get to the arterial, you may not want to use it. And as the system keeps evolving and get to the full automation, I think the transportation system's a major problem would be designing the behavior. How to tell the robot drivers to drive the vehicle for the maximum benefit of transportation users and travelers, and also the other people impacted and affected by transportation activities. So you can see the trend is actually learning the existing behavior to designing new behavior. That's what I think. So during this transition, the most intriguing and complicated stage would be the mixed traffic stage, where not only autonomous vehicles are on the road, but also human drivers and vehicles with different automations are probably involved in the traffic. So there are a number of studies investigating such mixed traffic behavior and also control, yet there are still a number of research gaps outstanding. So, for example, many of them have very simple assumptions. These sort of use the classic human vehicle driving behavior, actually stands for human-driven vehicles, and to apply that's for microscopic control, and which may not capture human drivers' uncertainties, stochasticity, and the heterogeneity. And also some studies about vehicle kinematics are highly simplified, like you could assume vehicles accelerate at an infinite rate, which is difficult to realize in real-world operations, particularly for microscopic management. And also the algorithms development, right now I talk to some industry industry partners who work in like leading AV companies like Uber, and they said that their algorithms are mostly brute force, although everyone's talking about smart learning algorithms. And also, I came in back from a conference where lots of people are looking into the same issues, but they were from other departments like computer science, electrical engineering. So they took completely different approaches than us, and they investigated the problems, think about the problems differently. And so there are some segregations of the research paradigms and methods, perspectives across different disciplines, even within the domain of engineering. And also, lots of the studies are just simulation or theoretical models, and there are not many published field experiments available to validate, test, and improve this kind of models. So we want to address some of these challenges. So where do we start with? We can look at a general trajectory control problem that is pretty representative to start with. So we have something specific to investigate, right? Rather than just hovering about the high-level problem scope. So let's think about just if there is a number of vehicles, some could be connected autonomous vehicles, CAV or modular vehicles. Some could be human drivers. All right, and we first consider longitudinal control. Let's say so. They start at some boundary conditions. They have each vehicle is indexed by I, and it has original location and sorry, there's a typo. This should be speed. Location and speed. That is their initial speed state, and also by the end, there is also some typo. This should be velocity v actually. Yeah. So by the end, they should get to certain. Oh, this is fine, I think. So by the end, they should want to get to a location that falls within a certain range. That's like their target. So they have some initial boundary condition and the final boundary conditions, right? So that's actually the boundary conditions. And besides, we consider some realistic physical limits, like we have speed limit, vehicles cannot back up, and we cannot exceed a certain maximum design speed. And then the accelerations are bounded by a finite range. You cannot instantly jump from one speed to another. All right, so the trajectories are kind of smooth. And also, we do not just look into one vehicle. We need to consider interactions between different vehicles. So along the longitudinal direction, there will be the interactions would be between every two consecutive vehicles, at least the first order interaction is there. So how do we represent the interactions between two CAVs? Let's look at two CAV trajectories. Xi minus 1 is the preceding vehicle, Xi is a following vehicle. So in order to ensure their safety, what we do is we shift the preceding vehicles by a reaction time 12 and downward by a sort of minimum spacing. And then we populate shadow trajectory, which is just like a shift, parallel shift of the preceding vehicle. And then what we want to have is the following vehicle's trajectory, whatever the CAV design is, we just want to keep it below this shadow trajectory. This would be able to ensure the driving safety. And the nice thing of this model is actually this is consistent with the Newell's scaffold model and the triangular fundamental diagram, which is a very nice model with lots of good analytical properties. And if you learn traffic flow theory with Dr. Bava, you may know nice properties about this model. And if you include human drivers, what are you going to do? So I see some studies actually, and I may also have some studies that just have some simple assumptions like I just use Newell's model with the shadow trajectories of the preceding vehicles, the following vehicle's trajectories. Just like the following vehicle could follow the preceding vehicle. And this treatment is really nice because it's sort of a group of human-driven vehicles and autonomous vehicles together. However many human-driven vehicles are following this fleet vehicle, you can consider it as a long vehicle, right? So with just like time and space shape. That sort of simplifies this analysis. You can use the CAV pure traffic methods to deal with this kind of mixed traffic. But of course, if you look into the microscopic detail, if you're looking into the rover data, it's not as perfect as that. Sometimes the deviation is high. So, I think you may really, if you want to incorporate uncertainties and heterogeneities, you might want to come up with some more advanced models, right? So for example, you need to include nonlinear area and stochasticity. One way to do that is come up with more complicated Kafala model with a bunch of linear operators for the current vehicle's trajectory and the preceding vehicle's trajectory. And you also add some random terms like what nodes, and you can do linear operations. I mean, when I talk about linear operations, you guys know it includes integral, differentials, and this kind of operations. So you can, so most of linear, actually, pretty much almost all linear Kafala models can be written in this form. And if you want to add some nonlinear area, you can put nonlinear function outside to construct this kind of functions. Of course, there are other ways you can come up with a more complicated model, like neural networks, which I've been talking with Dr. Lala this morning. But this way, you will be able to capture some of these uncertainties and unpredictability of that problem. And then you may need to come up with some new methodologies other than those readily available for pure CAV traffic optimization. So with that, what are we going to control for? So what kind of objectives we want to achieve actually? We've already talked about a number of issues like mobility, safety, and environmental impacts. We can construct the objectives to measure those impacts. For example, mobility, you can sort of maximize the distance travel, right? Which is another way to say minimize the total travel time for fixed distance. And then for fuel consumption, there are lots of instantaneous fuel consumption models. You can just do like integral summation to get fuel consumption value. And if you want to have something simpler, you can do like a summation of the acceleration, squared acceleration. You want to minimize that to sort of improve the driving comfort. And also, it is highly correlated with fuel consumption. For safety, one way is to ensure the safety constraints in the model, in the constraints, as I explained before. Another way is actually you can also put it in the objective, put some surrogate safety measures like time to collision or inverse time to collision, that kind of things, or even acceleration. You can come up with a bunch of safety surrogate measures. And with all these objective functions, you can come up with a general nonlinear objective function. Sometimes it may be non-convex. So then I can put back all these constraints subject to this objective function, and that is what this general problem formulation looks like. All right, I think if you guys are familiar with nonlinear programming, you may see something like that. So this is kind of like general models. I can give you some examples as like the special forms of this general model. One way is like vehicle docking or platooning, right? So we talked about connected autonomous vehicles, platooning, and also modular vehicles docking together like with zero spacing. And one problem is like if they're separated and if the vehicle units are separated and distributed in traffic stream, and you want to platoon or dock them together, how to control them to put that in a good way? What does that good way mean? So it means like minimize platooning time or docking time duration, and then energy consumption, maximize driving comfort and ensuring the safety, that kind of thing. So you see, they have the initial conditions are like they're separated and they have different speeds, and finally they're going to be connected together. Everything's going to be synchronized with fixed speed, constant speed, all identical speed, and also your spacings are sort of like become constant or stable. Another application could be joint signal trajectory control, and it is like one component of this is the general problem form. So this involves designing vehicle trajectories and also corresponding signal timing. And once the signal timing is given, the problem becomes designing the vehicle trajectories, which is a special case of the general problem formulation. And the signal timing is just the final boundary conditions. All right, so this you can see could be represented as a bi-level problems. And the lower level problem would be that's falling into the general problem formulation. And again, you're going to maximize this mobility indicators like throughput, driving comfort and minimizing energy consumption and ensure safety. Another application could be merging. So basically, you have different vehicles coming from different approaches. That could be, you can have them all pass, without stop or with stop. Whatever, this kind of merging section applies, or it could be a stop sign, interpreted as a general conflict area. And your objective is to maximize throughput and driving comfort, minimize energy consumption, ensuring safety. Okay. So all these different kinds of problems eventually roll down to this kind of formulation. And seems like it is pretty good to solve. It seems like if you solve this problem, it's like penicillin, you can solve all this problem. But it is actually a pretty complicated problem, right? There's stochastic term, and its objective is nonlinear, and sometimes it's non-convex. And it has differential constraints here. You're dealing with the trajectories where every point is decision variable. That means that decision variable space is infinite. Dimension is infinite. It's like you're optimizing problem with an infinite number of variables, which is really complicated actually. So how do we solve this kind of problem is what we want to talk about. So, and remember that we need to solve this problem on a matter of sub-second or seconds at most, because we're talking about real-time control. You cannot have a solver to solve it like half an hour or 1 hour, all right? Right? Okay, maybe a traffic incident will happen if you make it longer than a few seconds. So we need to come up with proper research methodologies or paradigms to look into such a problem. Okay, so let me just introduce my thoughts on the general approaches we can address this problem. So we basically look at the system like within the umbrella of the smart cities. So this system we talk about is mixed traffic flow control with automated, modular, and connected vehicles. But we may be able to generalize it to other systems with a similar problem. Okay, so we want to come up with a set of methodologies to address it. So first of all these methodologies, I want them to be centered at physics and behavior models with some analytical properties. Such analytical models would help us to give us insights to understand the model, understand the system. All right. So at least from the first order. If we can't capture the system behavior from the first order, and there are so many latent variables on captured information, you may want to use some data-driven approach to better understand the system, capture latent variables. And these two are complementary, but actually we may think of using some physical properties and behavior models to start some initial structure for data-driven approaches. And I'm going to talk about some thoughts about that later. And with that, we also probably need some mathematical programming, traditional optimization approaches to come up with solutions for not only understand, predict the system, but also control the system or measure the system. So we have heuristics, exact algorithms, and the analytical properties we have could come up with some construct some heuristics and also expedite some exact algorithms, and I'm going to talk about them later. And all of these will need to be validated by testbeds or tools, and also education and also technology transfer. These things wouldn't fly without a good demonstration that can reach out to the general public. So let's first talk about some physical and behavior models we're investigating. So it is a very complicated problem. Instead of directly solving it with a solver, which is probably not going to work for a problem that needs a sub-second or at least a second level response time. So we actually look into how to simplify this problem. First, we need to understand the general structure of that problem. So actually, we feel like for lots of these control problems, maybe the safety is the most important thing, because as long as you can specify the safety regions for vehicles to move around and maybe optimize the trajectories for the mobility and energy concerns would be easy to deal with. So we first look into the safety region or feasible region for vehicle to maneuver around. So we first look into one vehicle without considering other surrounding vehicles. So it has some initial conditions like beginning location, beginning speed, and also some final boundary conditions. And then we can use speed limit and acceleration limit to come up with a cone shape to define the possible region for this trajectory. All right, so basically this is a generalization of time geography theory. In the time geography theory, we only consider the speed limit but not acceleration limit. So a cone will look like a prism. But now after we consider the acceleration limit, this cone looks a lot smoother, all right? You don't get speed jump. But anyway, you can come up with a cone, and you have lower bound and upper bound of the trajectory movements. And you can represent the lower and upper bound in analytical forms, normally like piecewise polynomial functions. All right, they are pretty easy to deal with. And then we sort of like need to consider the interactions between different vehicle trajectories. So the way we look at it is, we could sort of integrate, sort of combine the upper and lower bounds of all the vehicles in a platoon. And because remember that the safety is defined with that parallel shift in consistence with Newell's model. You can shift them and merge different local upper bound and to form global upper bound, and merge different local lower bound to form a global lower bound. And then you know, with the presence of other vehicles, you can further reduce the activity range of the vehicles within this kind of a structure. We call it a global cone. All right. So you know, it is impossible for the vehicle to get outside of this cone without colliding with other vehicles. You can theoretically prove that. So then you can specify the range of this each vehicles, considering other vehicles impact. And the nice thing, again, because the upper bound and lower bounds in the global cone are also obtained by merging a bunch of piecewise polynomial functions, and the global upper bound and the lower bounds are also piecewise polynomial functions that are analytically solvable. So listen, you deal with a region where the bounds are analytically solvable, right? So, and with that, we know the range of this vehicle. So, at least we know the feasible regions or the domain of this kind of optimization problems. Besides the feasibility, actually, these bounds provide insights to optimality of the problem. Think about it, if you want to just address some simple objective, like if you just want to maximize mobility, all right? What you want to do is to pick all these global upper bounds from all these global cones, and then you can come up with a feasible solution that you can prove that it's going to be the solution that gives you the maximum mobility if you just want to define the objective as a way of like to cover the distance at any time, right? So because that's actually the maximum point that these vehicles can reach throughout the course of trajectory optimization, right? And besides, for other general models, we can also, these analytical properties have also nice implications. We're going to talk about in the next step. And with more general objective functions or other considerations, maybe it cannot be directly solved by analytical functions, all right? Otherwise they wouldn't be hard problems. So let's see how we address those general problems. So let's just consider simple case like with pure CAV traffic, all right, or the mixed traffic with Newell's alike model that you can simplify. sort of group vehicles together and make them like a heuristic traffic. All right. So with that, I think first we can come up with some fast heuristics. And actually, these fast heuristics can be constructed based on the feasibility analysis. So you know, because the bonds we constructed are like just a few pieces of analytical functions, we can think along the same way. Would we be able to come up with some feasible solutions with a few piecewise, with a few pieces of analytical functions that are not necessarily coincident with the preceding bonds? They may have smoother shapes, but they still follow that nice property. And this way, if we just deal with a trajectory that can be represented by a few analytical segments, then the variables are much reduced. Previously, every point is a decision variable. Right now, I mean, every segment can be specified with a few parameters, right? For example, if each piece is a quadratic function, you can specify it with 3 parameters, right? If you have 3 or 4 pieces, then 12 parameters you can specify, or 15 parameters, whatever, 9 to 12 parameters you can specify these trajectories fairly well, even less than that, considering the correlations between, connections between these different pieces, right? That's going to much reduce the complexity of the problem. Actually, we came up with a method called routine heuristic to utilize this kind of boundary condition. So the idea is we still construct these boundaries, but we use much milder accelerations instead of using the maximum accelerations. We can pick up, basically, we can just have a few acceleration levels, maybe that can be different across vehicles or can be the same across the vehicles. And we should let the trajectories share such parameters, and we use a few acceleration levels to control the overall smoothness of the trajectories. And then we can do a quick search across these few acceleration levels, and then we find the best solution with the best smoothness. And you know, with that, you're essentially dealing with trajectories that are composed of a few analytical segments. So, and they can be solved almost at a millisecond level solution time, which is good for real-time control. Besides the heuristics, you know, if some people are just as stubborn as me, who wants to look into the exact optimality of this problem, even for the sake of understanding the problem, you know, still we can use the analytical properties we just came up with to expedite the solution approach. So basically, these analytical properties give the global feasible region that is already a lot smaller than the feasible region originally specified by these constraints. We sort of like can utilize that to prune the solution space of the exact algorithm to further improve the solution speed. So we actually did some numerical analysis for the one type of problem we presented before. That's a modular vehicle docking. All right, so remember that different vehicles at different speed locations will dock together to form a sort of a train type like modular vehicle set. So, and we tried the exact algorithm. So we basically tried different instances. You don't need to worry about the variables. They're just to create different initial conditions. And we tried the original exact algorithm. We can put them into some kind of a solver to solve it. You know, and also we tried the model that incorporates the cuts provided by the global cones. Now we see the solution time is actually almost goes down to a third of the original solution time. That shows that okay, these cuts can effectively improve the exact solution. All right. So I mean, although for this problem syncopal you can get to like 0.5 seconds, but for other problems, We also tried other problems which may not get to this level of solution efficiency, but still the solution time can be much reduced. And so you may see that then the exact solution is not sufficient for the real-time applications, but it at least can provide insights into how close the heuristic solution is to the true optimum. If you have a benchmark, it can provide a benchmark to see how well this heuristic has done. Right? We actually compared the heuristic solutions with the exact solution. I think this is exact solutions. This is heuristic solutions, the second column. And we look into their gaps. I think their gaps are less than 7%, and on average about 5%, which is acceptable for engineering practice, I think, considering like the measures are not accurate. I think the error of measures, like if you talk about a few consumptions, it could go like 10 to 20%, right? So 5% difference is not that much. If you look at the solution time difference, this is the solution time of exact algorithm after expedition with cut space, and this is actually the heuristic solution. And these are conducted on my Chevy, personal computer, like that was 4 or 5 years old. But you can with fast heuristic, you can complete the optimal. You can get the optimal trajectories within 0.01 second, 10 milliseconds, or around that range. Okay, so that means probably good for real-time applications, right? So with this comparison, we know that heuristic algorithms are probably good options for real-time applications. We're pretty confident that their solution is pretty close to the optimality with a much better solution time. And we just do not just get satisfied with the analytical models. We did some experiments with robot cars, and I have some students who are really good at hardware, and they could use the embedded systems and electric magnet to do some experiments. We're still in the preliminary stage, and these vehicle controllers are not that stable, and the trajectory controller, and we need to find a better ways, but at least we can connect it together and separate, right? So and it's a pretty nice student project. So, and then you may, for more complicated problems, we may, in particular, if you want to realistically describe human driver vehicles, we may need to consider other methods. Like some people may say the learning methods, because that's like if you don't talk about learning, you will feel shy these days. So this is like a trend. But I think we need to put some cautions on using the learning method. I think the learning methods, they work pretty good for open systems with complex rules, latent behaviors, and stochasticity, that kind of thing. And not necessarily better than traditional methods like mathematical programming, MP I say here, for a well-defined closed system, all right? And not intuitive to incorporate some physics like safety constraints. And, so for pure traffic optimization, like I introduced before, I don't think it is extremely necessary to consider the learning. Maybe for some problems, maybe for some complicated problem, maybe it's still applicable. So because they have relatively little uncertainty, and the control, it is more about design of behavior rather than learning some latent variables. And you don't have much CAV data to learn. When we talk about learning, it's more data-driven. You don't have CAVs running on the street. And maybe you can collect, after Dr. Lava's project, we may have more of those. So I would, at the current stage, I would prefer using mathematical programming. But for mixed traffic, we have uncertain human behavior that may not be always perfectly described by Newell's deterministic model. We have heterogeneous drivers, and then we have more high-resolution trajectory data, and maybe learning would play a good role in it. And sometimes it can be combined with mathematical programming. So with this kind of beliefs or hopes, I actually explore some data-driven approaches. These are relatively recent work. And I think nice thing is we have good trajectory data sources that can describe human driven vehicles. We all know NGC, people who work on traffic flow may know next generation simulation data. I think Dr. Lava and I have both done lots of work with this data set. And we have limited range and relatively large areas. And if you're looking to microscopic properties, this type of microscopic, if you look into the acceleration and speed and the vehicle occlusion, you're going to find errors. And but the nicest over these years, we also collected some good data with our own effort, collaborating with other institutes. And for example, this is an experiment we conducted along sort of freeway, and it's not very busy, so we can hire like 13 or 14 vehicles to follow each other, and with a lead vehicle, roughly follow a certain speed profile, and populate some oscillations, or we can collect the trajectories over time. And these trajectories are miles long, and you can do some learning with that, right? So I think I think I should upload this data online to be sure. Actually, I've already uploaded some data online on GitHub. Let you know later. And also, there is a recent ongoing project. We're about to wrap up with FHWA, actually. They wanted to collect some railroad trajectory data across different sites, 4 sites, and actually tens of sites over 4 freeways in the U.S. Some are in Washington, D.C., some in Florida, some in California, some in Maryland. One signature thing is we want to collect 1.5 mile long segment. It's like much longer than NGC data. So, and we actually developed some tool for DU-based trajectory extraction. And we worked with a company who has state-of-the-art video system, like a combo set with 3 8K cameras. And we can cover 1 mile segment for 2 hours long. I mean, in the middle, they missed some minutes of data. And we're actually wrapping up with the trajectory data, and I think FHWA will publish it sometime next year, if not to the end of this year. So we're still processing some of them to correct some errors, but I think the data quality are much better, and this is part of the data we constructed recently. Nice thing I want to mention is this. It's a long story to get the good equipment like that, but this equipment is meant to shoot Hollywood-grade movies like this one, The Wolf, Wall Street, if you happen to watch it. So with this kind of data, actually, we could do lots of learning. So before the data were available, we still did some simulation-based work. So actually, this comes back to study working again with FHWA back in 2014-15. It is like they were having a huge project about speed harmonization, and we're a part of that, helping them develop the algorithm. So the problem is like you have some sensors and the vehicles in the transportation system, and the static sensors can measure the traffic throughput speed, and the perp vehicles can give you several trajectories. With that. And you have some CAVs distributed in this traffic. With the downstream sensor measurements, you can sort of perceive the downstream traffic patterns, predict the traffic patterns. And then with that, if you perceive a slowdown shockwave, you can smooth that, or at the bottleneck, you can smooth this CAV trajectory to make it just smoothly merge into, or avoid this shockwave, or at least merge into the queuing in a smooth way. All right, that's the idea. And the method we propose to FHWA is to use some simple models, like Newell's model, to predict the trajectory of the preceding vehicle to each CAV. And that is actually not that difficult for traffic flow students, right? Newell's model, you have 2 detector, 3 detector, and plus this kind of vehicle trajectories, you can easily construct the trajectory like this. It's not, and then with that you can do the optimization, and then you can do this construction and optimization in real time, dynamically updated, and then you can do hopefully you can smooth the vehicle trajectories. We did simulation, and it looks like This is the without speed harmonization, the queue is going to form, and this with speed harmonization is going to definitely queue formation in this. And in some ideal cases, it can provide some good improvement, and it improves the throughput and the fuel consumption by a few percent, and it decreases the speed of variations a lot, which means better safety. And also, which means better safety measures, all right? So, and also the FHWA did some experiments, but I tell you, they didn't use the original version of our algorithm because probably they didn't learn traffic flow theory class very well. They felt like Newell's model is still too complicated for them, actually. So they used a very simple, without feedback loop type of control. But they did some demonstration with their fancy Cadillac fleet. They have like 5 Cadillac vehicles, I mean, these 5 you see, and to do some experiments in open freeway, which is almost closed because that lane is sort of like there's no other traffic, or some other field tests. Actually, you can find the video over. This is some field tests. All right, and then recently, after collaborating with some institute, we have some access to the real-world experiment environment. So now we can investigate like coordinated trajectory control for given traffic signals. Let's optimize the trajectory for one vehicle in mixed traffic stream, hopefully to smooth the traffic and get you like smooth traffic patterns. All right. So instead of using Newell's model, actually, this time we wanted to try some learning. So we started from something simple, a Q table, which is not a high-dimensional method. All right, it's just like instead of using confounding models, we come up with a table that originally captures the real-world data, because they have like real-world test facilities. And for example, we can have some simple input like number of vehicles in the downstream, which we assume can be detected by downstream sensors or connected vehicle equipment, and also the immediately preceding vehicle speed. We have 2 like state of the downstream vehicles, and then with that we can predict and also the signal timing. All right, and such information can be passed on to the CAV, and then we can construct a Q table to sort of predict the exit time and speed and sort of like overall trajectory shape of this immediate downstream vehicle, and then we can. Okay, with that, we can control its trajectory in a similar way. We can use a shooting heuristic or a similar heuristic to construct a trajectory, to come up with like piecewise linear or piecewise polynomial, or just the one polynomial function to follow, actually.